From the Empire State Building to the CCTV Tower, many of the world's iconic landmarks are steel structures. Steel offers unrivaled stiffness and ductility per unit mass. A lighter steel member in place of a heavier concrete one can offer the same function at a fraction of the volume and weight. However, it will also have a lower total thermal mass. Over time, this has led to the widely held perception that steel structures must be protected against fire.
This perception has gained credence directly as a result of the traditional prescriptive approaches of designing steel structures for fire resistance. It is solely based on material behavior under high temperatures. It requires the temperature of structural steel to be maintained below a critical value, ensuring that at least 50% of the material strength remains available under the design fire.
This design fire has traditionally been represented simplistically by a time temperature curve. While this approach increases the cost of steel construction, it does not provide quantifiable structural performance against the real fires. Meaningful estimates of structural performance can only be determined by considering the architectural layout, field density and distribution, and structural interactions of all components. Such an approach can deliver quantifiable estimates of real structural performance and therefore safety against real fires at a lower cost.
Fire affects steel frame composite structures in two fundamental ways: weakening of the material and heat-induced forces and shape changes in structural components as a result of thermally induced expansion and bowing. For example, steel beams and composite floor systems designed to bend under loads may deform in fire to act like a washing line or a hammock to continue carrying load despite the loss of strength from heating. This mechanism provides additional safety to the structure, enabling it to withstand very severe fires without failure or collapse. However, traditional design approaches have focused on the material strength and have largely ignored thermal deformations. Therefore, both the beneficial and detrimental effects of thermal expansion are neglected in design. Modern methodologies of design, referred to as performance-based approaches, do consider all of these aspects of structural behavior in fire and result in safer buildings while also delivering savings of up to 40% in fire protection costs, such as in Plantation Place, Heron Tower, and the Shard in London, and numerous buildings in Europe. Despite the natural redundancy available, it is important to account for the effect of thermal deformations and alternative load path during the design phase. If we design structures neglecting these effects, we could potentially compromise safety by unwittingly enabling collapse mechanisms specific to fire. This is even more likely if we do not consider realistic fire scenarios and exclusively depend upon prescriptive rules. This approach wastes fire protection through indiscriminate application. Worse still, it may not provide sufficient protection where greater protection may in fact be required.
Over the past 3 decades, we have been developing know-how in analyzing the response of whole structure to real fires. We have found that many steel structure members can be left with little or no fire protection while still providing the required level of safety. This knowledge-based approach results in safer and more cost-effective construction.
To achieve this, we have developed advanced computer programs to model fires, estimate how hot they make building components, and how that affects the components of a structure and the building as a whole. Using these tools, we can build large computer models of structures in order to simulate how the building would behave in realistic fires. Using such an automated and integrated approach, we have investigated major structural fire disasters and have found that we can, by smart structural fire design, prevent them.
The knowledge and experience that we have accumulated over the past 25 years of research is now mature and can be applied to practice using many software tools developed in parallel with fundamental research.
For instance, software developed at PolyU has been validated against a range of full-scale experiments and has been used in the forensic investigation of real building and bridge failures in fire, such as WTC building collapses, Plasco building collapse and Birmingham Interstate 65 bridge collapse. These tools enable a designer to analyze structural performance under hundreds of different fire scenarios. Using AI tools to automatically design optimum fire protection provides the best possible safety for a given cost.
Performance-based engineering is increasingly permitted by building codes worldwide. Therefore, you can build safer structures and extract increased profits from choosing steel as your construction material.